Okay, I think it's a good time to start. Hello, everyone. Welcome to our today's webinar held by the Department of BEEE of Hong Kong PolyU and SFPE Hong Kong Student Chapter. And today I'm of great pleasure to introduce today's guest speaker, Dr. Caiyi Xiong, to introduce some of his currently research work. Dr. Xiong graduated from USTC, and his research interest including the flame behavior and acoustic action. He's currently a postdoc at Fire Lab of Hong Kong Polytechnic University. I'm of great pleasure to work with him as his colleague, and I learned a lot from him. He is also good at the fire simulation and fire dynamic analysis. Okay, today his a webinar entitled "The Mystery of Acoustic Fire Extinction." I think it should be a very interesting story. Okay, let's switch the mic to Dr. Xiong.
Okay. Thank you, Jiehao. Yeah. Wait. Let me share my screen. It has my slides. Can you see it?
Sure, clear.
Okay. Hello, everyone. I am Caiyi Xiong. You can also call me Simon. My great pleasure to be here today and to have the opportunity to share with you some of the stories behind the new fire extinguishing technology using the sound. Okay, so I think we can start now. First, let me introduce my research background. So we can see different fires in our life every day, right? But we did a lot of research about the fire, and this research can be roughly divided into two branches. The one is called the combustion research, like the fire we use in the kitchen, right, to cook. And in the combustion study, what we want is actually we want to make the flame more stable, so the flame can produce more energy to help us cook or do some other things. Okay, so that's another branch. It is called fire safety. So in the fire safety study, what we want just to make the flame more stable, make the flame unstable, reduce the burning efficiency of the flame, better that the fire can be extinguished, so that we can reach a high safety level, right? So my research recently was mainly focused on the fire safety research. Okay, so let's see how can we commonly extinguish the fire in life. Basically, these are the common extinguishing agencies we use in fire, like the water, the sand, the foam, right? They are good, they are useful, I mean, but they also have some shortage. Like the first, we need to store large amounts of these extinguishing agency, right? So as to be well prepared before the fire occurs. Or in some cases, like the electrical fire, we cannot use the water, right? Because it may cause the electrical short circuits. Okay? So this agency, they only works for a special fire case. And also, in some extinguishing agencies, it has some chemicals which may cause the environmental pollution, right? So as a researcher about the fire safety, one of our targets is to continuously find the new and clean extinguishing agent, right? So let's see. I don't know if you have played like this when you are a kid. So, right, like what the girl did. I found it on YouTube. Interesting. What the girl did is that she is screaming at the candle flame, try to use her sound to extinguish it. And actually, this is not newly observed. And the interaction between the fire and the sound was observed a long time ago, but only 100 years ago, this phenomenon was first documented in this publication, right? So, but it recently becomes a hot topic because we imagine that if the sound wave or the acoustic wave can be used as a fire extinguisher, it can bring a lot of the advantages, brings a lot of the yes, like this. So like as compared to the traditional extinguishing agencies, we don't need to store the sound, a large amount of the sound, right, before fire. And also, like again, in the electrical fire, the sound wave can be very useful to extinguish, and not only the electrical fire, maybe the liquid fuel fire and other fires, right? And the loss compared to other extinguishers, sound is clean, right? It doesn't cause the environmental pollution, right? There are so many sound in our life. Yeah, so what we want to know now is that whether the sounds can effectively extinguish a fire. So let's see some previous research. Actually, what brings the sound-related fire extinguishing technology as a hot topic should start from the one project, maybe 10 years ago, supported by the U.S. Defense Advanced Research Projects Agency, the DARPA. Yes. So what they want to do is they want to test whether the sound wave can extinguish the fire. So this is how they did the experiment. They put a huge speaker, and the flame they use is a gas burner flame, use the methane, right? And between the speaker and the fire, there is a long tube, the stainless steel tube, so as to keep the speaker safe. If the flame was put too close to the speaker may be burned, right? And the results from this project, the main results is like this. The x-axis is the sound frequency they use. Okay, you can see they only use the very low frequency sound, lower than the 100 hertz. And the y-axis is the sound pressure required to cause extinction. So from this result, we can see first, the sound wave can effectively extinguish the gas fuel flame. And the second, which is much more important, is that if the sound wave we use, the lower sound frequency we use, the lower sound pressure is required to cause extinction, which means the low frequency sound is easier to extinguish the flame. Okay, and besides the gas fuel flame, in this research, maybe 5 years ago, this researchers they carry out another group of experiments to test if the sound wave can extinguish the fuel gas flame. Okay, in this experiment, they test maybe 8 or 10 different liquid fuels like the hexane or heptane. Okay, and this is the main results. And by this research, we can see that the sound wave can also extinguish the liquid fuel flame. And besides this, it is again found that, right, the low frequency is better to extinguish the fire compared to the high frequency. And the frequency used here is lower than 50 hertz, right? Okay, so now we check the gas fuel, the liquid fuel, and how about the solid fuel? Actually, the solid fuel fire, like the wood, commonly the wood fuel is hard to be ignited, like a thick wood. So what we did here is that we only want to check the small size wood fuel fire, like the firebrands. So what is the firebrands? Firebrands always occurs in the forest fire, and they are the flying and burning the small leaves and twigs, and will fly everywhere, right? So what we want to check that if the sound wave can be used as an extinguisher, can we install the speaker on the outer surface of the building so as to build a safety shield, which can effectively extinguish the flame, only the flame, like this. But note that we cannot extinguish a smoldering wood like this, like a cigarette. We can only extinguish the pure flame. Okay. So in our test, what we burn is like this: a small wood ball, and we will use a pendulum system to effectively control the flying velocity of the firebrands. Okay. So let's see whether the sound wave can extinguish the wood ball fire. And the sound we use here is a 100 hertz sound. And let's see. All right, the beautiful fire was again extinguished, and before extinction, the fire was shaking, right? And by doing this experiment, again, we can see that only low frequency sound can extinguish the fire, and the lower the frequency we use, also the lower pressure is required to achieve the extinction, right? And now we have checked the gas, liquid, and solid field, and how about some other thing? And yes, there are some situations we can use the acoustic way to extinguish, like the dripping fire or dripping flame. So the dripping flame is like the one produced when we burn the plastic bag. The fuel will melt and drip to the ground, and the flame will attach on it, right? So, and it's very useful like this. This is a comparison of the how can we use a video to show how effectively the sound wave can extinguish the dripping flame. What is the fuel we use to produce the dripping flame here is actually a leg of a plastic chair like this. So the sound frequency I remember we use here is only 80 Hz. So let's see the results. And yeah, now. Right, you can see if we turn on the speaker, there will be a low frequency sound field, and no dripping flame can pass this safety region, right? 100% the dripping flame can be extinguished, right? And it's very useful. And what we see is, again, right, the low frequency is better to extinguish the fire. Again, we observe it, right? So we have already seen different researchers that there are still some unsolved problems, right? The first is why the sound wave can extinguish the fire. The second is why only low frequency sound is better to extinguish the fire, right? So, is there any extinction mechanic we have? Actually, in this research, remember, use the liquid fuel fire as the targets. The authors try to explain the extinction. And this is what they observed just at the moment before extinction. Like the red region is where the fuel source. So you can see before extinction, the flame was deflected far away from the fuel source. Okay, based on this observation, the author says, okay, then maybe we can explain extinction in this way. This is the liquid fuel, and we burn it, and the fire is in it, right? So when there is no speaker, there is no sound wave, the liquid fuel can receive the radiation heat feedback from the fire. They can observe the heat and then evaporate as the liquid fuel and add the gas fuel source to support the flame, right? But when we turn on the speaker, when the sound wave starts to work, the sound wave may attract some air flames to below the liquid fuel, so as to cause the cooling effect to take the heat out from the fuel bed. So in this way, maybe we can explain the extinction as a competition between the fuel heating and the fuel cooling. Yes, this is an excellent way to explain this the acoustic-related extinction. But the problem is, at first you can see there is completely no sound parameters in this mechanic, like the sound pressure and the sound frequency, which means based on this mechanic, we cannot explain why only low frequencies effectively extinguish the fire. And second, what is the airflow caused by the sound? We don't know. If this is true, what can be the difference between the sound and the wind? We don't know, right? So that's inspired by this experiment. Remember this experiment? We used the sound wave to extinguish the dripping fire. We also tried to improve the mechanic. And this is the also the filter I put on my poster, right? This is the dripping fire. So let's only take one drip as an example. This one, okay? This is the dripping fire, right? And which we can explain the extinction of the dripping fire as a competition of two types. The first time is the time required for the flame to ignite the fuel gas, because the fuel here was only the plastic drip. So this time, the required time can be a constant. And another time scale is the time available for the time to ignite the fuel gas. So what's the meaning of this? Because the fire needs to always stay here to continuously ignite it. But how long can it stay in this region? And normally, if we want to calculate the time, we need two parameters. The one is the characteristic length and the characteristic velocity. And the characteristic length we have here, only one, is the diameter of the drip, right? It's okay, we can measure it. So how about the characteristic velocity of the flame? So let's see what velocity now works on the flame. It's a dripping fire. It's forced down. So first velocity, the fire has a falling velocity, the dripping velocity, right? And when the speaker starts to work, inspired by the previous research, we think maybe the speaker will cause so-called the sound-related velocity. We don't know what's that, but it's just a velocity, right? And this sound-induced velocity on the speaker should be the same on the one works on the fire, right? So now we can see there are two velocity components working on the fire. So in this way, we can know the characteristic velocity of the flame is a combined velocity of the dripping one and the sound-induced one, right? We can calculate it like this. So how to get these two velocities? For the dripping velocity, it's easy. We can measure it in our videos. It's okay, easy to get. And what's the sound-induced velocity? We don't know. What we can measure is only the sound pressure. So the pressure, the velocity, okay. Maybe we can use the momentum equation to calculate it like this: the square root of the ratio of the sound pressure to the air density. So by this mechanic, you can see we successfully introduced one sound parameter into this mechanic. Yes, only one, the sound pressure, but we don't know where the sound frequency works. This mechanic, you can explain why the larger pressure is easily to cause the extinction, but why the low frequency is better to cause the extinction. We still don't know, right? So based on these discussions, we know that, okay, in this research, there are still two problems we need to solve. First one, we still don't know why it is always easier for the low frequency sound to extinguish all the flames, the liquid fuel, gas fuel, all the flames, right? The second one, we want to know the exact difference between sound and wind, right? So to answer these two questions, we need to carry out another group of the experiment. Okay, so let's first explain the low frequency mechanic. Okay, in the new experiment, what we like to do, actually it's not candle flame. What we use here is not a candle. What we use here is a gas burner, a Bunsen burner flame. Okay, and the fuel we use is the propane. We will put the gas burner flame close to a huge speaker, and the sound frequency we use here is also very low, 50 to 70 hertz. Okay, and the sound pressure is also just in normal region, 0.3 to 3.2 Pascal. Okay, so let's first see what will happen if we just put the flame in front of the speaker. We turn on the speaker, but we only use a low sound pressure. We will keep the sound frequency at 60 hertz here. You can see with a very low sound pressure, the flame only shaking, right? And the fluctuation center line is same as the center line of the nozzle, right? Shaking like this, like dancing. So why the flame can shake in a sound field? What is the sound field? So this animation shows the particle movement in a pure sound field. So you can see there are two arrows. For the red one, the red particles, normally in the air when we speak, you can imagine it as the air molecule. So you can see in a sound field, the air molecule different from the wind. The air molecule only moves back and forth periodically. And the moving frequency is same as the sound frequency, right? And there is another arrow, the black arrow. You can see it's a wave, right? It's propagating. So this wave, you can think it's a fluctuation, but at a fixed phase, and it's propagating. So the propagating of the black wave velocity is commonly what we know the sonic velocity. Okay, so in those fields, imagine if we put a flame inside this field, what will happen? The air molecules will continuously push the flame, right, like the sea wave. So in this way, the flame can shape like this. Okay, but what will happen if we increase the sound pressure? Now we increase the sound pressure to a very high value, the 1.8 Pascal. So we can successfully observe the extinction of the flame, right? And again, you can see before extinction, the flame is also fluctuating. But in this way, the fluctuating center line of the flame is different from the center line of the nozzle, right? It was fluctuating with a random center line, right? So why is this? Let's draw a figure to explain it. So this is the original station of the flame, right? And when the speaker starts to work, the flame will first be deflected to a random average position. And because the periodical movement of the air molecule, the flame will continue to shake around this average position, right? So it's shaking in amplitude. We call it the flame displacement or the position displacement. We use delta F to represent it. Okay, then we can measure it. We can write a code to measure this flame position displacement. And the result was like this. The x-axis is the sound pressure we use, and the y-axis is the position displacement we measure. And the different points on this figure just means different frequency you use. So we can see that the louder the sound is, the flame was deflected far longer in a longer distance. And the second, what is more important is that no matter which frequency we use, the flame will always be extinguished when its displacement reaches a maximum value, a critical value. And in this experiment, the critical value is around 3 millimeters, right? Why the flame can be extinguished when it is displayed to a specific distance? It's just because at this flame displacement, the flame reaches its critical stretch rate, like a piece of paper like this. And if we stretch it enough hard, the paper will break like the flame surface. Yes, they are the same, right? So it was stretched and break, then extinction occurs. So based on this experiment, we can say, maybe this factor, this parameter, the position displacement, can be a key factor, help us to explain the low frequency mechanics, right? Because the extinction only occurs when the delta F reaches a critical value, right? So how can we understand the other characteristic of this position displacement? And by the right figure, we can first know that, of course, the flame position displacement should be positively related with the sound pressure, right? Okay. So any other characteristic of this displacement? We need to carry out another group of experiments. So in this experiment, we will fix the sound pressure. We only change the sound frequency. Let's see the results. And yes, right. When we change the frequency, the larger the frequency we use, the flame critical displacement is decreased, which means this flame position displacement is further negatively correlated with the sound frequency. Right? Let's combine these two observations together. First, we know that delta F can help us to explain extinction. And the delta F, the flame displacement, is positively correlated with sound pressure and negatively correlated with the sound frequency, which means we can write it like this. So the P here just means the minimum sound pressure required to cause the extinction, which has a unit of Pascal. And the F here, which means the critical extinction sound frequency with a unit of Hertz. So in this way, by this equation, we can roughly know why the low frequency sound is better to extinguish the fire. And for a specific value of the delta F, if the lower frequency we use, right, only a lower pressure is required to keep the delta F as a constant, right? Can we explain the low frequency volcano in an easy way to understand? We can try. Do you still remember the sound field we introduced before? It's like a C wave to continuously push the flame, right? Then we can imagine this sound field and the flame like this. We can imagine the sound field as a boxer who is continuously puncturing a sandbag. And the sandbag, we can imagine it as the flame, right? So in this way, when this boxer is just puncturing at a high frequency, which means he hits fast, right? So the force of each punching can be very low. And in this way, the sandbag can only be pushed away with a short distance, like the flame is slightly shaking. So in this way, the flame cannot be extinguished. But if the boxer just puncturing at a low frequency, so the force of each pump is very large, right? So in this way, the sandbag can be pushed to a far distance, like the fire can be deflected to be far away from the fuel source. So in this way, the extinction occurs. Okay, and this is also the reason why only the low frequency is better to extinguish the fire. It has a larger pushing force. Right? Okay, and we have a lot of the data. We collect them from, I remember, more than 10 papers, and from the experiments using different, like the fuel, like the gas fuel flame, the solid fuel flame, liquid fuel flame. Okay, and this figure is a three-dimensional figure. The vertical axis is the extinction pressure with the unit of Pascal, and the two horizontal axes, one is the sound frequency required to cause extinction with the unit of Hertz. And the last one, originally it should be the flame displacement, but we know that the flame displacement is hard to be measured or observed by our eyes, so we just replace this with the flame height. It's okay because the higher the flame, the larger the displacement is required to cause extinction, right? Okay, so based on the three parameters, we can get a fitting like this equation. And so you can see this equation very easy, and it has a very good, the R squared is very good, almost reaches 1, right? So based on this equation, we can easily estimate the critical sound environment required to cause the extinction, right? For example, there is a fire with a height of 0.1 meter, and we want to use a 50 Hertz sound, and what is the pressure we need to cause the extinction? You can calculate by this equation. Very, very easy to use. But what we need to mention is that this equation only works for buoyant flame, which means the fire or flame can only be dominated by buoyancy. This equation cannot be used to the jet flame, like the engine flame, because this flame is dominated by the momentum. Okay. Yes, you can try this equation. Okay. Now we already know why only low frequency is better to extinguish the fire. But we still want to know the exact difference between sound and wind, right? Let's re-examine the flame extinction in a sound field like this. Okay, so you can see before extinction, the flame was deflected far away from the fuel source, like there is a strong wind below it. not only in the industrial experiments, like the DARPA test videos, like this. All right. Right. Before extinction, the fire was also below, far away from the fuel source. So which means the sound seems can attract wind, but I mean there are so many sounds or noise we can hear every day. Have you ever feel the so-called sound caused wind or airflow? Can you feel it? Maybe no, right? So this causes us, this inspires us. When it is true that the sound wave can really cause the extinction, or the extinction is just caused by some other factors, right? So we need to do another group of experiments. So in this experiment, we just use candle flame. Okay? A thin candle flame. It is stable, and there is a wind to support the flame, so the whole flame can be exposed to the sound wave. And we will put the candle flame in front of the speaker. And what is different is that we will also put a sound meter around the flame to continuously measure the sound pressure at the flame position. And we will use just a thin aluminum panel to help us. To just put it, in some cases, we will put the thin aluminum panel between the flame and the speaker so as to separate the flame from the sound field. Let's see what happened. Okay. Yes, well, we only use the 60 Hertz sound. So in this case, we just increase the speaker power to produce a fixed sound pressure as here is measured on 97.3 decibels, right? You can see in this case, the flame was deflected far away from its peak, right? Almost reached the extinction. Okay. Now let's keep all the conditions same, but only put the aluminum panel between the speaker and the flame. Let's see what happened. The panel is here. So can you see? When we put the panel between the flame and the speaker, the fluctuation of the flame disappears. But now let's recheck the sound pressure here. The sound pressure is still very high, 96.3. Okay, only with the decreasement of 1 decibel. Right. So let's further check whether the disappearance of the flame fluctuation is indeed caused by the decreased 1 decibel. So we do that, we just remove the aluminum panel and reduce the power of the speaker. We reduce it to produce a lower sound pressure, just at the 96.3. Okay, so let's see. Right. Without the panel at the 96 decibel, the flame fluctuation appears again, right? So based on this simple experiment, we think, okay, since the flame fluctuation or flame extinction is not caused by some pressure, right? Seems the flame extinction is caused by some other factors. And this factor can be blocked by the aluminum panel, but the sound cannot be blocked by the aluminum panel, right? So what the aluminum panel can block should be a wind. There should be some other factors in the speaker to cause a wind. So what is this? Let's recheck this experiment in the front view, okay? So you can see during the extinction or during the fluctuation, the flame is shaped. And what is another factor that is shaking is the front surface of the speaker, right? The speaker diaphragm. Yes, seems, and you can see, observe it again. And the flame and the speaker diaphragm seems they are fluctuating at the same frequency with the same altitude, right? Yes, maybe there should be at least 2 fields in front of the working speaker. The first one should be a diaphragm-induced wind flow or the wind field. The second one is what we say the sound field, right? Seems if it is not the sound field that caused the extinction, it should only be the diaphragm-induced wind flow to cause extinction, right? To further confirm it should be the diaphragm-induced wind to cause extinction. Remember what we measured before, the flame positive displacement, right? Yes, in that experiment, we further measured the displacement of the membrane, and we compared. Yes, then we found, yeah, they matches with each other well in different sound conditions, right? Seems the membrane-induced wind should be the right factor to cause extinction. So how about, but previously you told us it should be the air molecule that is also moving back and forth periodically, right? And the air particles, they are also fluctuating with a moving distance. So how about the particle displacement? Yes, in a pure thought, the displacement of air particles we cannot measure, but we can calculate based on some acoustic theories, like this, okay? And we calculate it and put it in this figure. Where is it? It's here, right? And please note that the y-axis of this figure is not a linear axis; it's a log axis, right? Which means the pure sound caused particle displacement is very small. It is 100 times smaller than the displacement of the membrane, right? Which means compared to the diaphragm-caused wind, the sound, the moving distance of the pure sound is very weak, right? So how can we understand there are two sound fields in front of the working speaker? Like you can imagine now I'm speaking here and you just stand in front of me. We are very close to each other. Now I'm speaking to you. You can clearly hear the sound, right? And by the way, you can also feel the air coming from my mouth, right? So these are two fields. But if you stand to a long distance from me, like maybe 5 meters away, you can still hear my sound, but you cannot feel the air from my mouth because they are dissipated, right? And based on all experiments, we know that it is not the sound to cause extinction. What causes extinction is just the air from my mouth or the wind caused by the fluctuation of the speaker membrane, right? That why you may say, well, the fluctuation of the speaker diaphragm is so easily to be observed. Why it cannot be observed in previous flags? So do you still remember in all previous flags, they will put a long tube between the speaker and the flame so as to keep the speaker safe and not to be burnt, right? Yeah, it is the tube, you will cover the surface of the speaker and covers diaphragm. So nobody can observe the fluctuation of the diaphragm. What they can observe or what we can feel is only the sound. So in all these previous work, they only think, okay, it is just the sound works on the flame, right? But actually, there is a tube in front of the speaker which reduces the spatial dissipation of the wind. So actually, it is the diaphragm caused wind to cause extinction, right? And what can be the influence of the tube? Like we can try to estimate the influence of the tube. Like now, there is a speaker. We put a tube in front of it. We want to extinguish the candle. So now we know that inside this tube, there are two factors works. One is the sound, another is the diaphragm caused wind. Okay, and now we know it is the wind to cause extinction. So in this case, maybe we only need a low sound pressure to cause extinction. Maybe the sound pressure is around 100 decibels. Okay, we can bear it. But if we remove the tube, we keep all the conditions same. We just remove the tube. We know that the air, the diaphragm caused wind will be dissipated, but the sound can still be transported to work on the flame, right? So do you remember previously we say the fluctuation of the sound particle is 100 less than the fluctuation of the diaphragm caused wind, which means we need to increase the sound pressure so as to increase the displacement of the pure sound particles. So in the second case, in the lower case, which sound pressure we need is around here. And you can see, oh, maybe it's only increased from 100 decibel to 140 decibel, not so much. But what I need to tell you is that 140 decibel is same as the noise level when an airplane takes off. It's hard to be hard to be bear. It may permanently here damage. It may cause permanent damage on our ear. We may be deaf, right? So in this way, we can see by a pure sound, the pure sound is very difficult to extinguish the fire. Only the diaphragm-caused fins works for the all previous acoustic extinction. Okay. Yes. Now, based on this discussion, now we can know. Okay, actually, the so-called the sound-induced extinguishing technology, and actually it's just like the wings below us of the fire. Okay. Yeah, that should be the main summary of this presentation. And finally, I need to. This is not only my work. I need to thanks for all my colleagues working in PolyU, and also thanks for the support from the SFPE funding and the PolyU funding. Okay. And again, that should be all my presentation. Thank you.
Okay, thanks, Simon. I think it's an impressive and great work because you solve a problem which is commonly ignored in previous research. And okay, so for our attenders, please feel free to leave your questions and comments on the chat box. Okay, and firstly, I want to say I have a question. At the page of where you propose the critical distance, I think it's 3 millimeter. 3 millimeter, yeah.
Oh,
I forgot the number, but I remember the
value. Here?
Yeah, this page. Yes. I think it's good to propose such a critical value, to quantify the critical condition for the fire to extinct. And my question is how the value will be affected by the test condition. I mean, you only demonstrate your work with a candle flame. So with a burner. Will the heat rate, the fire size affect the critical value? Do you have any future plan on it?
Yes, because you mentioned there are some other parameters to describe the fire, like the fire heat release rates or the fire size, right?
Yeah.
Commonly, just mean a larger fire, a shorter fire, the flame height. A larger fire should have a larger height. A small fire should have a lower height, right? A larger fire, of course, the pulsating displacement should be larger. It's like the paper, we need to use a more force. We need to stretch hard enough to break a hard paper like this. Yes, they are always positively correlated between the heat release rate and flame height and this pulsating displacement. Yes, different flames should have different critical displacement.
Yeah. Okay. So I also have another question on the on the whole work. I mean the acoustic field is I think it's with very high uncertainty, and I noticed you use some error bar to quantify the uncertainty in your work. Yeah. Okay. Uncertainty. Yeah.
Yeah, like this error bar.
Yeah, you use some error bar. Okay. Yes. So how you treat those uncertainty? Will the uncertainty have a very large effect on your work?
Oh, it's okay, because you can see the uncertainty here, because the unit here is only millimeter.
Yeah.
Actually, the uncertainty is about maybe 0.01 millimeter. Okay, that's amplitude. Right. They will not bring great importance with great effects on results. Yes. It's okay.
Okay. Yeah, thanks for answer. And we receive a question from Zilong Wang. Okay. Can the acoustic extinction work for momentum controlled fire?
Momentum controlled fire, you mean the jet fire, like the engine fire? Yes. Yeah. Yes, because at the beginning of this presentation, I said most of our work will only focus on fire safety research. And the flame in fire research, they are almost always the buoyant fire. And the jet fire was always used in combustion research. So in combustion research, we don't want to extinguish it. That's the first answer, right? And the second is, you can imagine the burning rates and the flame heights of the jet flame should be much larger or stronger than the buoyant flame. I don't think the weak acoustic or wind can easily blow out a jet flame. It's kind of hard. difficult. Thank you.
Yeah, because it's driven by different force. One is buoyancy in your work, and
Yes.
there is another story if the fire is driven by the momentum. Okay, thank you. And just for curiosity, do you have any future plan to apply your conclusion, your research work output to commercial use?
For commercial use, yes. Yes, because we found that pure sound cannot extinguish the fire. Right? What is useful to extinguish is still the wind, right? So maybe in the future plan, we still need to do some researches about using the wind to blow out the flame, or just use the sound. We can use sound not to extinguish, just for example, detect the flame. Yes.
Okay, so
thank you.
Yeah, so it's not only for the fire extinction, but also for the fire detection.
Maybe, yes. It could be.
Yeah, no, great idea. Okay,
Mhm.
so no more questions. I think it's the end of today's webinar, and all the attendants will receive your certificate in maybe 1 or 2 weeks. Okay, again, thanks for Simon for your clear and impressive lecture, and thanks for
thank you.
Yeah, thanks for our attendants for coming. Yeah, bye bye.
Okay, thank you. Thanks for listening. Bye bye.